Our second ideal gas law example we want to look at today considers a situation where we initially have a gas sample stored under one set of conditions. Then the conditions change and the gas sample has the opportunity to expand. We want to determine how many moles of the gas will stay in the container. So in this question, which again comes from an outside textbook, we are told that a 250 milliliter flask open to the atmosphere contains 0.0110 moles of a gas at 0 degrees Celsius. Upon heating, some of the gas escapes. How much gas would remain in the flask at 100 degrees Celsius? All right, so in this case, we're clearly given two sets of conditions. In our flask initially, which is open to atmosphere, we have 0.0100 moles of a gas. The temperature is 0 degrees Celsius, which is the same as 273 Kelvin. The volume of our flask is 250 milliliters, and the external pressure is 1 atmosphere. When the flask is heated, because the pressure remains constant, since it's still open to atmosphere, and the volume of the container remains constant, some of the gas escapes the flask. And we want to figure out how many moles of the gas are still in the flask at a higher temperature. So because we have heated the gas now expands, it's free to escape out the top of the flask, and less gas, fewer number of moles, remains in the flask than was in the flask initially. All right, so in terms of our strategy, this seems like it's setting up to be, we do the ideal gas law at 0 degrees Celsius, and then we do the ideal gas law again at 100 degrees Celsius. But if you look closely at the information given, we are actually given enough information regarding the initial conditions that we actually know everything about the flask under the initial conditions just based on the text of the problem. We know the volume of the container. We know how many moles of air were in the flask. We know the temperature of the sample. And indirectly, we know the pressure because we're told it's open to the atmosphere with no further information supplied. So we assume that the pressure is 1 atmosphere. All we need to do is determine how many moles of gas remain in the flask of conditions, 100 degrees Celsius or 373 Kelvin. The volume of our flask hasn't changed. The pressure of the system hasn't changed, but some of the gas has escaped. And so it's important to remember that when they ask how much air remains in the flask at 100 degrees Celsius, they're asking how many moles of gas are still in the flask. So in terms of our strategy, all we have to do is solve the ideal gas law under the second set of conditions to determine the number of moles of the gas that would remain in a flask with a volume of 250 milliliters. The ideal gas law says that the pressure volume product is equal to the moles times the gas constant times the temperature. Once again, we will rearrange the ideal gas law and solve for the number of moles. And so in the numerator, we have the pressure volume product. In the denominator, we have the gas constant times the temperature. And we just need to calculate the number of moles. Before we get into the calculations, we need to make sure that all our measurements are in the right units as usual and make sure we have the correct value for the gas constant. The gas constant R is 0.0821 liter atmospheres per Kelvin mole. The pressure is still 1 atmosphere because the flask is open to the atmosphere. The volume of the flask was originally given to us in milliliters, so we have to convert milliliters to liters. Remember that there are 1,000 milliliters in a liter, and if you do the unit conversion, you'll see that 250 milliliter flask is 0.250 liters. So we have to make sure that our volume goes in there in liters and that our temperature goes in there as Kelvin not Celsius. 100 degrees Celsius plus 273 give us a Kelvin temperature of 373. Now all that's left is to do the calculation. 1 times 0.250 divided by 0.0821 times 373. There should be 0.008164 moles of the gas still in the flask at the higher temperature. We're entitled to keep 3 sig figs. Technically, we are only given 1 sig fig in the 0 degrees Celsius temperature measurement, but since our other temperature measurement has 3 sig figs, we calculated it under these conditions, and so we're entitled to 3 sig figs in our answer. 0.00816 moles of the gas remain in the flask.